Welcome to that lecture online, and now we're going to take a look at Gauss's law and electric flux and see how there's a lot of similarity here between the two concepts. Here we have the equation that represents Gauss's law. If we have an object that has charge on it and we draw a Gaussian surface around it, we can say that the integral, the surface integral of the electric field strength, or you should say the electric field at the surface dotted with dA, which means dotted with the surface area, we take an integral over that is equal to the charge inside the Gaussian surface divided by epsilon sub naught. So since the electric field strength and direction, and especially I should say, since the electric field direction is in the same direction as the perpendicular line away from the surface, the angle between those two vectors, E and dA, are 0. Therefore, the cosine of 0 is 0. Therefore, we can say that the integral of that is equal to the strength of the electric field times the area of the surface, which then has to equal the Q inside divided by epsilon sub naught. Now, it also turns out that if we have, for example, a surface, and we have electric field going through the surface, and of course the electric field emanates from positive charges, negative charges, but if the electric field is present where that surface is, we know that the electric flux, which we write like this, the electric flux is going to be equal to the strength of the electric field times the area of that. And so we can think of the Gaussian surface as an area through which the electric field emanates, so therefore the electric flux here would also have to be equal to the strength of the electric field at the surface times the surface area of that surface. So in this case, that would be equal to the electric field strength at the Gaussian surface times 4 pi r squared, which is the area of the Gaussian surface. And you can see the similarity between this and this, because we can also say here that E times the Gaussian surface, which is 4 pi r squared, I forgot the closing bracket, equals Q inside divided by epsilon sub naught. So therefore, since this is equal to the electric flux through the surface, we can say that the total electric flux through the Gaussian surface is equal to Q inside divided by epsilon sub naught. So that's another way of looking at the total flux through the electric field. Now what's interesting is, notice that the total flux does not depend on the radius, which means I can go farther and farther and farther out. The total flux emanating from this, going to the surface, will always be the exact same, depending on the charge inside divided by epsilon sub naught. Which makes sense, because we can see here that close by, the electric field lines are much closer together, so therefore the field strength is greater. And as you go farther and farther and farther out, there's a lot more surface area over which the electric field is distributed. Therefore, the density of the electric field lines diminishes. The density of the magnitude of the electric field diminishes, but the total number of flux lines does not change. They're just farther apart, field gets weaker, but the number stays the same. The total flux through the Gaussian surface will always be constant, determined by this. So that's a really nice insight that we get also from the Gauss's law.